Hi there, welcome to a lesson on sequences. In this lesson we will do a mixed problem set of problems related to arithmetic and geometric sequences. Let's get started. First of all, these are the four main formulas you should be familiar with. Beginning with the arithmetic sequences, we have the nth term formula. This is a formula that is used to find any future term in an arithmetic sequence. The d represents the common difference, or the value that each value in the sequence goes up or down by, and u1 is our first term, and the n, of course, is the future term at some position. To find the sum of an arithmetic sequence, we use this formula. This formula gives you the sum of all the terms. For example, if you said s sub 8, that would mean the sum of the first 8 terms in the sequence, and that is found by doing this. Here we have term 1, here we have the final term of the terms you want to do the sum of, and that's the formula there. Now let's look at geometric sequences. The nth term formula for geometric sequences is this, where r represents the common ratio, or otherwise known as the multiplier, which is used to change from one term to the next successive term. u1 again is our first term. And then we have our sum of terms for the geometric sequence. This formula here, it is used to find the sum of some number of terms in a geometric sequence. Again, we have the r value, the common ratio, and term 1. Let's use these four formulas now in this problem set. Problem 1. Here are the first 5 terms of an arithmetic sequence. What would be the sixth number? Well, I hope that's pretty obvious once you look at the sequence. It's going up by 5 every time, therefore the sixth number will be 26. Now calculate the 50th term. And now calculate the sum of the first 50 terms in this sequence. Okay, so right away we're told this is arithmetic sequence, therefore we know we're using these formulas. In B, we're looking for the 50th term, some unknown future terms. So we're going to use the, let's go back. We're going to use the nth term formula as it is used here to find u50, the 50th term. Notice we put in the d value here of 5. We put in term 1, which is 1, and then 50 is our n value. You should get this value here. In C, we're asked to find the sum. So now we're using the sum formula for arithmetic sequences right here. The sum of the first 50, so 50 over 2. We put the first term here and the 50th term here. Well, we already know the 50th term from this work, so that 246 goes there, first term, multiply, and we get this sum of the first 50 terms. Next problem. Here you have a geometric sequence and we are given the first 3 terms. What is the common ratio for this sequence? Well, you may have said it's a -3, and that makes sense. The way to find the common ratio is to take one term and divide by the previous. In this case, to find the ratio, I did u2 divided by u1. You could have also done u3 divided by u2. That common ratio is -3. After finding the common ratio, you're asked to find the sum of the first 10 terms. So here's the sum formula, which is, again, we're looking at geometric sequences now. So here's the sum formula here. We put u1, our first term right here, -2, and then 1 minus the common ratio, which we found to be -3, to the n power, which is 10, and on the bottom, 1 minus the ratio. On the bottom, be careful, we have 2 negatives, which will make a positive. But here, that will not happen, because we will apply the 10 to this first, and then do 1 minus that result. So be careful how you work with negatives. Next question looks like this. We have the first 3 terms of an arithmetic sequence. So again, we're going to be using these formulas, and we are given these 3 terms. Notice the terms are given as algebraic expressions instead of just values. So if you look at that, you're looking at this first term, second term, third term, and it says show that k equals 2. Now in math, when we're asked to show something, it's like a little proof. That means this is the result we want to get for k, but we cannot take this result we are given here and put it into here to check, because that's the first thought some students have is, oh, k equals 2, so they put it in here, here, and here. And then they'll get some kind of sequence. But you can't take this thing and put it in. You have to work with what you're given and arrive at this result without using this during the process. So we know that in an arithmetic sequence there's a common difference. So what would be the difference between these first two terms here? And how about the difference between this term and this term? You can find that by doing u2 minus u1 or u3 minus u2. So how about try that? Create two situations where you've done this minus this and this minus this, and that's our common difference. But our common difference must be the same. So set those two common differences equal to each other and solve for k, and you should arrive at this. Okay, I hope that worked out. So now that we know that k is 2, we can move on to b. In b, we are finding the first three terms. Well, in that case, now we have proven k, so you can put it in here and find the first three terms. Then write down the value of the common difference, calculate the 25th term, and find the sum of the first 25 terms. Okay, let's check all that work now. So here's what I was explaining in terms of a, in terms of finding the common difference, right? We can do u2 minus u1, okay? And we can also do u3 minus u2. That simplified works up to this, and this one simplified works up to this. Again, be careful with the negative sign, because here you will do minus k, and then you will also do negative 4. So 5k minus k is 4k, and 2 minus 4 is negative 2. Over here, same thing, we have the minus sign here. It applies to this and this. So 10k minus 5k is 5k, and negative 2 minus 2 is negative 4. We, as I said, the common difference must be the same because it's an arithmetic sequence. So this can be set equal to that right here, and we get k equals 2. Great, that was that work. Once we know k equals 2, we put it in here, here, and here, and we get our sequence 6, 12, 18 with a common difference of 6. Then you're finding the 25th term using the nth term formula right here. It's being applied right here. And then you're finding the sum of 25 terms right here. All right, let's take a look at the next one. Here we have a geometric sequence with second term 21 and fourth term 5.25. We have learned two kind of approaches to solving problems like this. Let's see if you can use one of those approaches to find the common ratio and then the sum of the first 10 terms. All right, here's one approach to that. We know we have the fourth term and the second term. So I'm going to write one kind of recursive rule using the fourth and second term. So to get the fourth term, we know we begin at the second term and multiply by the common ratio twice. And that's why we have r squared. Because to get from u2 to u3, we multiply by r once. And then to get from u3 to u4, we multiply by r again. So from u2 to u4, we multiply by the ratio twice. It's like 2 jumps from u2 to get to here. So 2 jumps means 2 multiplications of r. Okay, so now substitute what we know. We know u4, we know u2, and then we can solve here for r. So first I divide it by 21. I have this. Oh, I wrote it twice for some reason. And then you take the square root of that to get 0.5. Now, one thing we should know here, and this is important in this question, is that whenever you're taking a square root and solving for a variable, you get a positive and a negative answer, because 0.5 squared will give you this, but also negative 0.5 squared will give you this, because negative times a negative is positive. So both of those are possible r values, and that's important when finding the sum of the first 10 terms, because we are going to apply this sum formula for geometric sequences twice. We're going to do it once, assuming that r is 0.5. So you can see this blue matches this blue one here. R is 0.5, and we get this value. But we can also find the sum, assuming that maybe the r was actually negative 0.5, because it could be here as well. So now you can see that negative r values put in here, we get a different answer for the first 10. And that makes sense when you go back to the sequence, because the sequence, we have the second term, fourth term. If we go from the second term to the third term, you can multiply by either a positive or negative value to get the next or third term. And if you did that by a negative r value, the third term would be negative. If you did by positive, it would be positive. But let's say we did use the negative r value, so we have a negative third term, and then you multiply by negative r again to get a positive term here. So even though that middle term between 2 and 4 can be either negative or positive, the fourth will still be positive each way. Think about that a little bit. Okay, let's try another one. So here's a question where we're given another arithmetic sequence with 20 as the 6th term and 50 as the 11th term. So similar to the last question where you know one term and then some other term in the sequence, but this time we're talking about arithmetic sequence. So see if you can solve that. Okay, let's check. So we know U6 is 20, U11 is 50, and now again I wrote kind of a recursive rule connecting U6 and U11. So I know to get from U6 to U11, I need to do 5 jumps. I'm going to jump past 5 terms, right? To U6, to U7, to U8, to U9, U10. That's 5 jumps. And each jump in an arithmetic sequence is a common difference. So we go U6 plus 5 times whatever the common difference is, and then we get to U11. So I put in my U11 here, my U6 value here, and I'm solving for D. So solve this, and you get D equals 6. Now that you know the D value, you can find the first term, because we need the first term to find the sum of the first 100 terms. Because in that formula, the sum of terms in an arithmetic sequence, we need the first term and the future term. So again, we know D. I'm putting it back in this formula here. Oh no, sorry, I wrote a new formula. And this one's kind of a reverse of this one here. Right, this one was showing us how we get from U6 to U11. Here's how we get from U6 to U1. Right, to get U1, we begin at U6, and then we do minus 5D, because we're doing like 5 jumps backwards in the sequence. So minus 5D, and we'll get to U1. So U6 was 20. Let's go back. U6 was 20, and minus 5D, we know D is 6 from here. And that means 20 minus 30. Negative 10 is our U1 value. Now we need the 100th term, because this formula also needs the last term. And we're finding the sum of 100, so I'm finding U100 using this formula, the nth term. So U100, and I get that to be 584. Now I have all the pieces I need for the sum formula, which is first term, last term, and then 100 over 2, because we're doing a sum of 100. There's our sum, big number. All right, I think there's one more here. Let's try this one. Okay, here we have a geometric series. It's given to us like this. All right, we know some terms and then dot, dot, dot. So this is some future term. We don't know which one it is. So you might want to start by figuring out how far into the sequence is this one. Let's check our work. So first I'm also finding the R value, right? So I'm doing U2 divided by U1. You could have also done U3 divided by U2 and so on. But that gives us our common ratio, our common multiplier, which is negative 1/2. And that makes sense here. Every time we go here, we're doing half the value, but it's also changing negative to positive, so it has to be negative 1/2. Okay, that's our R value. Now I'm going to use the general rule for geometric sequence, and I'm going to plug in our future term of negative 3/8 here. I know our first term is negative 96. We know our R value, we just found it here, and we're solving backwards to get n. Now we've done things like this a few times when we don't know n and we need to solve n. It's in the exponent. We can use something called logarithms, but we haven't learned that yet. So we can also just guess and check some values. So here I guessed some values, I put different values for n, and finally when I got to n equals 9, I found out it works. This side equals this. So n equals 9. So that means to find the sum of these, I need to find the sum of 9 terms, because that's 9 terms in total. So I'm doing S of 9 using this formula right here, calculating it, getting this result. Make sure you can punch all that in your calculator. Okay, I think I said that was the last one, but guess what? There's 2 more. Last 2 are kind of word problems, but the math behind them is pretty simple. See if you can read this and work this out. Okay, and now check your work on that one. Okay, here's U18, and here's the sum after all those years. And last one, we have this one here. Population is growing. And this one is going to be a geometric sequence. Let's see if you can figure it out. Okay, here's the setup. Here's the population, some unknown one. And here, to find U3, I set up U1 times R squared, because it's going to be 2 jumps, and check the work for the rest of it. I hope you are able to understand that.